My name's Dave Stiver. I'm a PM in GCS during the day. Sort of my daytime job is looking after different parts of object storage on GCP, which is a great part of my job. My nighttime job is sort of looking after AI workloads across file, block, and object, which we've been spending a little bit of time on that over the last 24 months. So really happy to be here and tell you a little bit about the cloud storage side of things. We're going to go through each of these different phases of the AI data pipeline. We'll start specifically and talk about training, and then checkpoints, and then inference. So starting off with training and cloud storage, I want to talk about just two features within cloud storage that we're going to walk through. One is GCS FUSE, Cloud Storage FUSE, and the other one is Anywhere Cache. Before I get into the specific features, I just want to talk a little bit about the people who are doing this work and making sure we orient around the developer. So when we talk to our customers, both the ML developer and their bosses, the most important metric to them is time to serve. So they've got somebody who's working on building a model. He's sitting there on his desktop. He or she is trying to figure out whether this is actually something that they can use. And that is the most important metric. The scalability, the performance optimization, how it works, all of that comes down the road. And so all of this leads us to this very clear point of view. Those folks don't actually speak object. Those folks speak file. And so it's really critical. We realized this, a few years ago, is that on top of object storage, which is incredible from a cost and scalability perspective, you have to have a file interface. And that's what FUSE is, right? Is really just an adapter on top of cloud storage to be able to mount a bucket and present it to a user just like it's a local file system. We've made large investments in Cloud FUSE really over the last 2 years, but we've accelerated that with everything that's happened in the AI world. And so from a performance perspective, there are two specific things that we've done in the last year. The first is a local cache. And so now when you use GCS FUSE and you're downloading data onto, let's say, the GPU host itself, those GPU hosts often come with SSD. I think on the H100s today, you can get 6 or 9 terabytes of SSD. So now there's a cache. So if you're doing multiple reads on the same data, we cache that data locally on the machine. The other thing that we've done is create parallel downloads, all just to speed up that performance for getting data from GCS onto the local host. So both of those things now have shipped. And I wanted to walk through another example. We'll come back to GCS FUSE, but another area where we've been spending a lot of time is with this new feature called Cloud Storage Anywhere Cache. We started talking about it maybe towards the end of last year, and then really talked about it in detail this spring at Next. But Anywhere Cache, you can think of it as a SSD local zonal cache that's built directly on top of GCS. So you read your data out of the bucket with all of the same APIs with FUSE or with a GCS API, and we cache that data locally within the same zone as the accelerator. So you can think of this really as the way to bring your data off of disk in a GCS bucket and bring it into the same location that your accelerators are in. It's our first zonal product actually within cloud storage. So we're very excited for a couple of reasons. One thing that we're using this for primarily is to achieve very large amounts of bandwidth. So if you think about what we can do within a region versus within a zone, if we bring that data directly close to the accelerators, it's just easy to scale bandwidth. And so out of the box, Anywhere Cache will have, I think, 20 gigabits per second per terabyte of cache size. So, and the initial cache size for this product is up to a petabyte. So that's about 20 terabits of bandwidth that you can get from a single zonal cache. So when Sean was talking about that large scale, it's not for everybody, but for somebody who's operating at a very large scale, who needs a lot of read bandwidth from cloud storage, Anywhere Cache is really incredible. The other super interesting thing about that, and I don't know, for folks who may not be as familiar with cloud storage as other products, we have 3 different kinds of locations that cover different kinds of resilience. So we have a regional bucket where that data is in the same metro, but we also have multi-region and dual region buckets. One thing that we're very excited about is the ability for customers to store data in a multi-region bucket that we place, sort of anywhere within a continent, and then they use Anywhere Cache to boost or lift that data directly to wherever they happen to find accelerators. And we wish everybody wishes there were more accelerators, and so they can be in short demand. And so this is one way to put your data, store it one time, and then bring your data to wherever you happen to find accelerators.
Quick question,
Yeah.
just to be sure, that anywhere cache is then a cache in another region, or where is it located then?
Yeah, so you can use it, like think of it in two different modes. You can use it with a multi-region bucket and then cache that data in whatever region, actually whatever zone your accelerators happen to be, and you can create multiple caches in multiple zones. Or
you can control yourself.
Correct. Yep, okay. Customer chooses. And then another mode is just on a regional bucket. Say you've got accelerators and a regional normal GCS bucket in one location. You can use this instead of having just a regional product, now you have a zonal product to scale that bandwidth. So it works in both modes.
Okay.
Yeah.
Thanks. Is it a consistent cache? Like strongly consistent, eventually consistent? Like what's the consistency model of this cache?
Yeah, so you're reading like second time read. So if you cache miss, you're just reading back to the bucket. Like you read first time, we load that data, and if that data is not there, we're always going back to the bucket. So
if the data changes,
if the data changes, you go back to the bucket.
Okay.
Yep. Okay. Let me talk a little bit about one of the use cases for FUSE. So this is a customer of ours. I don't know if you're familiar with Woven, but Woven is sort of the autonomous driving division of Toyota. They reached out to us maybe the end of last year, beginning of this year, and started talking to us about coming to GCP. And one of the things they were really interested in is getting their data into cloud storage and using that for their training jobs with all of their autonomous data from their cars. So they have they've invested a huge amount of effort in building up their own MLP, internal machine learning platform. And that's built on top of cloud storage. And so they were very excited about the use of FUSE and how they could use that to accelerate their workloads. So we just wanted to walk through that use case with you and actually let them tell you about their use of it. The first thing they said to us in coming is we would love to actually be able to use cloud storage in lieu of Lustre. Like we use Lustre today, it's highly performant, but it's very expensive. And one of the things they were able to do with FUSE and the local cache is actually replace many of their Lustre clusters with GCS FUSE. And that is not to say that GCS FUSE is going to be the same performance as Lustre, but it was sufficient for them in order to meet their needs. And so they found up to 50% reduction in their overall training cost. And 14% reduction in their training time, which for them is actually more important. One of the things they shared with us in sort of doing that transition, and this transition, they're fully on board to GCP today, is just managing those instances is actually a challenge. So one of the things they love about cloud storage is just putting their data in cloud storage and then using FUSE to access it whenever they need to.
Hey, Sean,
yes.
Sean, sorry.
Yeah.
The 14, okay, so you said that it wasn't as good as Lustre, but yet you're putting up there 14% less training time. So
what they found is that comparison is with and without FUSE. So what they got is the comparison with cloud storage FUSE with that local cache. The local cache was something that we just released in the spring of this year. And so that was the comparison they were making. That was the difference. They were actually, I think, probably our first customer for that local cache capability. And so both of those things together is what made the difference for them in their particular workloads.
Okay. And this is all just training, just pure training?
Yeah, this is all just loading training data. Okay. Exactly. Here's actually just a little bit more deep dive on that if you want to look at how that cache works. This chart is really just a comparison of what happens in the load times for the first epoch and the second epoch during a training job. So you see that the top plot is the first epoch. We're loading that data, and you can see the plot there shows like all of the reads directly out of GCS. For the first and the second epoch, they're the same. And then with the local cache is the bottom plot. So you see the first, like you have to load all the data. But then once you've loaded that data, everything on GCS like drops to zero. All of that data is local. So not only are you, you're getting a faster load of the data, it's already there. You're not paying all those operational costs like you would normally. So that's part of the performance and savings benefits. Yeah, please.
Can I just ask one more cache question
Please.
real quick? So
Yeah.
it looks like the cache is tied to either region or multi-region, whichever, and then I might have multiple of those. So like, how does the cache invalidation work cross regions?
So the cache can be used in all three. We have three different region types. We have a regional, a multi-region, and a dual region. In multi-region and dual region, you're using it locally in those locations. The multi-region is the only case where you can cache in different locations. That's sort of the benefit of multi-region, is store one time and then use in each location. There's no difference in behavior for the cache between those different.
I think my question.
Maybe one of the things. The other thing is like those three bucket types that Dave just described are all viewed as a single bucket. So even though you have the data in two regions, it's a single bucket view for how you're going to use it, and that might be your consistency question.
There you go.
Because it's whichever of those three types you choose, you're always going to have strong consistency to access the correct data to then serve up and cache maybe in a zone in a potentially different region based upon.
Sorry, yeah, I should have covered like those GCS, but they're all like single namespace, like highly consistent. Like, we take care of that, so that bucket has one name. We take care of replicating that data into each of the locations.
That's what I was saying. Like we invalidate here in this region still reading from cache. Like
correct. That's one of like the I would say major differentiations in cloud storage is those products and that capability of having that that view across different locations.
But like let's take an example. So if you have an object that is cached in this cache, and it is deleted from other path because it is multi-region, multi-zone, it is deleted from the other path, and this cache is not aware that this object is deleted, and somebody looks up this cache, it will get the object, right?
No, that cache actually is aware of that. Yeah. The cache actually is aware of it. It is consistent.
Yeah.
Okay.
Yeah.
Okay.
Yeah. And I'll say, like, for some workloads, that's really critical. For AI, like for training data, it's not nearly as critical, right? Like most of the data for training data, like they get a snapshot of that data, we're going to train against that, and then that training data doesn't change over the course of that job.
Right.
Not true for lots of other workloads, analytics, and other things, but
right. So the delete has to propagate and invalidate all other copies of this object in all other cache.
Yeah. The other thing like about that is like the metadata is consistent across that location.
Yep.
So whether it's the cache or the bucket, that metadata is consistent across all of those different deployments.
Okay.
So thanks, Dave and Sean, for introducing the conversation. My name's Dean Hildebrand, second Tech Field Day. So glad to be back. As part of this, or as my role, I'm a technical director at Google's Office of the CTO, working on our storage and infrastructure strategy, and most notably, as of late, as you can imagine, around storage for AI has been a huge area of my focus. And I'm really happy to, as Sean said, announce Parallelstore, which we GA'd this week. It's our very first fully managed parallel file system offering, targeted towards the HPC and AI workloads that need extremely high throughput, but also low latency I/O operations. As someone, Sean said before, I'll just sort of say, so this is built on DAOS technology, which we are now a part of the DAOS Foundation, which is part of the Linux Foundation, and that's something that we're really excited to grow the open source community there as part of this. And so while, on-prem there are installations of DAOS greater than 100 petabytes, we're starting relatively modestly as our first fully managed parallel file system. So scaling up to 100 terabytes and around 125 gigabytes a second. And so why is this important, right? We talked about some of the different workloads through that Dave and Sean were talking about. But I think the key point is there is no AI ML storage workload. Like there is no one workload. It is a vast set of workloads depending on how the application was written, the type of application they're using, the input training data sets that they're accessing on. And so what we're seeing is that especially when a user has been using a parallel file system on-prem for all of their workloads, then when they try to migrate into cloud, they have written it in a way that not only needs the file-based interface, but also has created hundreds of millions of small files or is reading really small I/O out of larger files. And so that type of general behavior and expectations from the training job then is something that is enabled through Parallelstore. And so that's been our key focus, is to really differentiate the offering in that area. And then in addition to that, though, it is a scratch-based offering, which means, it'll stay up, and I think a mean time between failure is, in the 3 to 6 month range. So we're really targeting it towards offerings where you're running a training job for days, weeks, maybe a month or more, but then you just shut it down, and all of the data that you've generated can then be stored back in GCS. And so that's why we've really made the data movement between cloud storage and Parallelstore so super easy through integrated APIs and an auto tiering based capability of that. So I actually have a demo that I want to show as well. And so what our demo is doing is integrating with some other tool part of our infrastructure called the cluster toolkit. And so what we found is that, back to the AI supercomputer that Sean mentioned earlier, this sounds good. You get all these different pieces, but if you're going to build something on your own, it turns out it's pretty complicated, as you can imagine, to deploy all the compute networking storage and then your scheduler and configure it all together and make it work with a cohesive system. And so the cluster toolkit is this modular Terraform-based system that just really simplifies the entire process. And so what we've done is integrated that with Parallelstore as well. And so that's the demo that I'd like to show you now. All right, so let's kick it off. All right, so what this is that every cluster toolkit solution starts off with what we call a blueprint, which is just a YAML file that describes all of the different resources that are needed to be deployed in the system. This is an example of using our HPC images called H3 mixed in with a Slurm scheduler. And so it has all the different pieces in here that are needed for that. And we have all of these blueprints that are available online. And so you don't have to create this from scratch. You can just pick the one that most closely matches what the type of environment you're looking for. So here you can see we've added in a Parallelstore section. You can list the mount options that you're needing for the different types of workloads. But then as well as you can list that source bucket that I was referring to earlier in terms of where the data, the source data will be located. And then scrolling down through all the different resources, you also see, so not only do we need to deploy a Parallelstore instance, but we also need to actually connect it in to all the compute nodes. And so this is something then that we have done through a single line change in the Slurm controller setup. And this basically just says, make sure that whenever you're launching VM types on our platform, that it's integrated and mounting the file system to make it accessible. And so a couple points there then is, again, this is like an H3 plus Slurm example, but we also integrate with all of our GPU and TPU instance types, as you can imagine, but then also with our Google Kubernetes engine. So GKE is also fully supported in this environment. So if we hit deploy now, we have a G-cluster tool that effectively takes the YAML, generates all the Terraform, and then deploys all of the resources and configures them to make sure that all of the networking and everything else is set up. And it takes a few minutes. We'll jump through it, though, quickly here. And so once this completes, what we want to do is just demonstrate that, one, we have a Slurm cluster and it's up, and you can see the resources are H3 based that it would launch. And so these aren't actually launched yet. Well, there's 2 at the moment, but it can auto scale to launches to as ever many instances are needed. And then the other thing we want to validate is that the data was in fact copied into the Parallelstore instance. Well, it was created and then copied. And here's just an example of how we copied in some baseball stats into the file system. Obviously, if this was an AI training job, then this would be the training data set that got automatically copied in. And so this is a key point, because you don't want to start the job and have it sitting around waiting for data to be copied to the local SSD or to somewhere else, right? So you want to make sure that when the job launches on the GPUs, which is the majority of the cost, that all of the data is ready to go and it's not sitting there stalled. And so this is something that we've really integrated into that flow in both the GKE and the Slurm context. And then now that we run a job, and this is just a simple job to create some files on the different nodes, this is just demonstrating that the file system was in fact mounted in and is accessible from all of the different nodes. And so in the AI training context here, what would really be shown is that the job can run, can access all of that data that you pre-populated, but then in addition to that, you can generate the checkpoints as often as you need to. And one of the key advantages of the parallel file systems is that they can saturate the NIC of the TPU and GPU nodes, so you can checkpoint more often or as often as needed. And that is the demo. So thanks to everyone there. All right. So that's Parallelstore. But as I mentioned, first, we focused on making it a scratch offering that integrates with GCS so that you have the best of sort of the low cost of GCS, but then having really fast systems available when the jobs are running. But we also have users that are looking for bigger and faster systems. And so that's why we've worked with our partner SciComp to deploy IBM storage scale in the marketplace. And this is something where SciComp has really taken the sort of guesswork or all of the complexity out of this deployment. Everything is automated. All of the configurations are tailored for our environment. It works with both GCE, our compute types, as well like standard and the Slurm type environments, as well as our Kubernetes, GKE type environments. And brings in all of the enterprise features, again, that someone mentioned, like 20 years of, the management, compression capabilities, and all these different types of things. And it also brings in that flexibility, so you can choose the type of storage you want to deploy, the type of compute you want to deploy, and really scale it up to large scales. But the other reason that I think third-party options are always going to be around in cloud for AI and ML is that a lot of users are looking to build hybrid deployments. They're buying on-prem DGX clusters and they're integrating them in, but they need a single source of truth in terms of how are they going to manage all of the huge amounts of data that they have in this hybrid environment. And that's where storage scale really shines, because it can integrate into our buckets, or it can integrate into an on-prem system that's sitting there. And so it can dynamically bring in data from on-prem. It can dynamically bring in data from the buckets as it's accessed. So this is something where it's not just the size and scale, which is an important point, but also brings in that hybrid and multi-regional aspect into the system.
Are you seeing customers using that, since it's on-prem and it's also in the cloud? What are the use cases they're looking at?
Yeah, so just imagine there's a few different use cases, but a traditional one that we have some customers on, they have an on-prem DGX cluster. They have an on-prem file system. It actually doesn't have to be storage scale on-prem. It could be any file system that's being used there. But they either want burst capabilities into Google, or they just have, like, what we're seeing is that the demand is so high, very quickly burst has become the new norm. And so now they're just running in cloud some percentage of the jobs at all times as well. But the challenge comes in is like, well, where's the source of truth, right? So is it the on-prem file system? Is it the cloud storage bucket? And so this becomes a way where we can either have the on-prem system as the source of truth and then dynamically bring in data from on-prem using storage scale, or you could set the cloud bucket as the source of truth and both have them feeding from on-prem and in cloud resources out of that bucket. Does that make sense? Yep, awesome. So I think some of the best practices here on the training side is, one, work with our partner SciComp, because they've just made this so easy out of the box as opposed to trying to go in it alone. But in addition to that, it's really about working with them on the configuration. You can make it a persistent and building on our hyperdisk block storage offerings, or you can also build scratch-based offerings on like our local SSD and might be increasing the perf per dollar, but with the idea that it is a scratch-based system. So these are some of the key things to think about when we're deploying it, and like the use case, and then the amount of data that they're and the performance they're looking for. All right, so then I'm also going to talk about Hyperdisk ML, which is our next generation. Hyperdisk generally is our next generation of block storage that we've launched in the last year or so. And Hyperdisk ML is extending this into a world where you can create a block storage volume, make it a file system like ext4 or something to that effect, load it up with training data or a model, and then launch that out into the full cluster, up to 2,500 instances in this case, and up to over a terabyte a second. And so the sweet spot here is really around if you don't have that much data, you don't have tons of jobs running on the system, but you do need to have that level of performance that scales out let's say, a relatively small amount of data out to large numbers of training instances, then this becomes a reasonable option to think about, because you don't, when you think about other systems that are usually in the terabytes or tens of terabytes, hundreds of terabytes, petabyte scale, and then this can scale down much lower in terms of that.
What's the scale of a single volume?
So you can go, I can't remember what the smallest is, but you can go down to, I think like 10 gigabytes or something to that effect, maybe one, I can't remember the smallest, but the largest, it can go up to like 64 terabytes, I believe. But I'm sort of just highlighting the fact that it really shines when you sort of have that smaller amount of data that needs like the higher level of performance, like that balance, if that makes sense. Some of the things to watch out for as well, though, on HTML is that it is a read-only data set, right? Once you create the volume and you attach it into the other nodes. And so in order to take advantage of this, if they're coming from on-prem or something, they're going to have to change their workflows in order to figure out how to fill up the block device and then attach it to all the different instances. And we've made that easy through GKE and other systems, but it's something to watch out for in terms of that workflow, because once they've done that, then once they filled in the instance, then it cannot be changed until it's like detached and from all the instance types. All right, so I think that's the end of the training section, and now we were going to move on to checkpointing, which is obviously an integral part of any training job, but kind of has its own nuances.
So just a couple things about checkpoints. The workload is quite different, and so from a cloud storage perspective, we want to make sure just some simple things like separate your data, right? Do not have training data and checkpoints in the same bucket, because you may have different ways that you want to manage that data. That's pretty important. As much as possible, when you can get to asynchronous checkpoints, particularly with cloud storage, because of the performance, that's the best thing. As the industry is moving forward, what we see is more and more of the frameworks are now beginning to support async checkpoints, because the models are getting bigger and they're realizing, oh, we do not want to block training on writing this checkpoint. So that's starting to come into fruition.
So are the frameworks kicking off the checkpoints then?
What's that?
Are the frameworks kicking off the checkpoints then?
Yeah.
You're doing an API call to the...
Yeah, a lot of that is
device?
encoded in the different frameworks.
Okay.
And so we see PyTorch, and like we've been making a lot of investments in JAX, obviously, but PyTorch has actually just, I think maybe a few weeks ago, announced that they had support now for async checkpoints as well.
Okay.
Yeah.
So how do you recover from an asynchronous checkpoint? It's if you're trying to restart that job from that checkpoint, it's how do you get to that point if it's an asynchronous checkpoint?
How do you read back, or?
Well, how do you restart the job at that checkpoint if you don't have the necessarily consistent checkpoint?
Sorry, when we say async, like that nomenclature, just means that you're not, like, it's still consistent at that point in time. Like, that's written out, and the frameworks do that work by writing locally to the machine and then offloading to their storage system.
Okay.
So like it's still consistent.
Okay,
It's async just means that like you're not pausing the training job.
Okay.
So it's like non-blocking.
Yes, not blocking.
Yes, not blocking. Okay, thank
But
you.
what can happen in that case is that your async checkpoint is running, it's not complete, and you can have a failure before that.
So it's really important to be able to write and successfully write that checkpoint. So as part of that library of checkpoints, you actually have to know and make sure that you have a
Return it.
like, yeah.
Otherwise, you have the older checkpoint and then you can roll back.
Exactly. Yeah, there's this really, like, maybe it's interesting or not if you've been in this space before, right? It's just like with the model scale, like the model scales up, the number of parameters scale up, the number of nodes goes up, and the failure actually rises as well. And so the importance of creating like high frequency checkpoints in order to recover. And we have this term called good put, which is just how it's essentially the efficiency of the training job. Think of good put as like if it were 100%, it would mean you were never paused. Once those accelerators start going, you were never pausing. But when you have a failure, and that failure could be a hardware failure or it could be a failure of the model, right? The model may diverge and you have to recover. Every second that you spend recovering that, like loading that checkpoint back, is just inefficiency in the training job. So super critical part of the overall efficiency story, especially for large scale jobs. At smaller jobs, less it can be less important. One thing I just wanted to point out is what we see from our customers is they think about checkpoints in two different modes. There's the checkpoints in their development work. So you have an ML researcher and they're playing around with something, and like those checkpoints are essentially their IP. Like what they tell us is we're saving those checkpoints and we are never getting rid of them ever. Like this is actually our IP, and so we need to they need to be protected. But we also want to hold on to them forever, and we're probably not going to go back to most of them. And so AutoClass is a feature that we have within cloud storage that allows you to automatically, we take care of automatically down tiering your storage to the coldest storage classes. So AutoClass is great, along with Soft Delete for protecting development checkpoints, that I would say. Like when you're doing a production training job, those are just useful over the course of the training job. So what we would recommend is turn off Soft Delete. You probably don't need AutoClass because you're not going to hold on to that data for longer than a month. And so you just sort of two different configurations depending on the kind of work and where you're at in the pipeline. Developer versus the ML engineer who's now taking that model and is running it in production on a recurring basis. Okay. Oh, last point, I did want to make this point, sorry. Cloud Storage Fuse, which is incredible for loading data, right, for writing checkpoints. We actually don't recommend the use of Fuse for writing checkpoints. We are introducing a new kind of bucket called an HNS bucket or a hierarchical namespace. So GCS buckets historically are flat. They've been flat for 20 years. We're finally putting some structure in them from a performance perspective. That feature is going to go to GA, I think, later this month. So GCS Fuse with hierarchical HNS buckets will actually be great for that. So if you're planning to use it in the next few weeks, don't. But if you wait a few weeks, you'll be fine.
So in terms of whether the file interface or the object interface is used, like what's the percentage in terms of AI workload catering only the file and versus the object interface?
Yeah, this is like a metric that I stare at all the time. Because like we kind of every day look at the adoption of Fuse and how quickly it's growing, and it's just like it's gigantic. Like we're sort of taken back by how strong the growth is. We certainly have large scale. If you're looking at cohorts, I would say small to medium sized customers with small to medium sized training jobs are completely using Fuse if they're using cloud storage to load training data. For the very small number of very large customers, they've done optimizations and they're using, for one reason or another, they've been able to do their own like specific optimizations using our APIs or using something that they built themselves, a custom data loader. So I would say think of it in those two cohorts. We definitely have customers who have optimized even beyond what we've done in Fuse, but Fuse should be the first place that most customers, 95% or more of customers, should think about.
Okay.
Yeah.
Kurt, here I got a question for you. You're talking about difference between early model development, self-delete, auto-class. It might seem that like companies will end up in situations where a lot of times they're not even sure if like they want to hold on to that stuff or keep it. Like maybe you're going to talk about this with how Vertex starts helping out with stuff like that, but like, are you doing anything to help people in app better understand what their needs are and where they should be putting things and what settings they should be?
Yeah, I didn't plant that question, but like one of my colleagues, Manjul, is who just joined, is going to talk about that later in a session and talk about sort of management at scale.
Yeah.
The wonderful thing about cloud storage is it's easy to get to trillions of objects and exabytes of data. Super quick, super easy. The challenge with that is it's easy to get to trillions of objects and exabytes of data. And so we actually built like a specific new API just to be able to actually keep track of what that looks like. Yeah.
Yeah, so looking at checkpoints for the parallel file system area. So I think the important thing here is, really driven at the original set of the training workloads. So if they've decided that due to the workload or the APIs that are required or whatnot, that a parallel file system is needed for training side of a house, then it just makes logical sense to use it for the checkpointing as well. We have a big thing about like, don't waste IOPS, right? So the IOPS are prepaid for in the parallel file system world. You get these IOPS whether you use them or not. And so making sure to leverage all of the read and write bandwidth of these systems is always something that we encourage customers to do. And it usually happens quite naturally anyways, because no customer just has one job running at a time. They have different researchers running single node jobs, plus large scale training jobs happening, plus a whole bunch of other types of activities that might be happening on the data set, like data prep in the background. And so when all of these jobs are combined together, then the IO mix back into the file system is usually quite balanced in terms of the read and the write side. So I think that is like an important sort of thing on deciding when to use the parallel file systems. And then as well as, again, on the Parallelstore side, since it is started off as a scratch-based offering, using the import-export APIs to save those checkpoints back to GCS long-term storage. Or on the storage scale side, they have integrated methods through which you can just take specific directories, map them down to buckets, and then certain directories, as Dave was saying, you don't need, this is more experimental type work, you don't need to save those, just leave them around. And other directories can automatically be replicated into the object store for long-term.
So, Dean, are the checkpoints differential? Or
so you mean in terms of how the synchronization happens?
Yes.
Well, checkpoints, once they're created, typically they're non-modified, right? So it's like the memory dump, if you think about it, from all of the GPUs in the cluster or the TPUs. And so once that's created, then no, typically, right, the next one is literally all of the memory again, right? So each checkpoint itself is its own sort of entity.
Okay. So it's not based on differential snapshots. It's like complete. Every checkpoint is so that would require a lot of flushing of data back again for every.
Yeah, I mean, exactly. And so this gets to the point of how often they want a checkpoint, how many parameters are in their model, determines to some cases how big the checkpoint is, how many nodes they're using. So we've talked to some customers that only, they consolidate all the data down to, let's say, 25% of the cluster nodes, and then they just write from there just to make it very efficient and to stream out data. So a lot of sort of factors go into when choosing on what system you need. The key thing I think on the parallel file system side is if they're happy enough with the read throughput that they're getting, which each node can saturate, that NIC. So we have 200 gig NICs today, and you can get the 20 gigabytes a second performance out of that. On the right side, it's the same thing, right? They can write down at that level. And so that's faster than the local SSD that they might be writing to if they were trying to do a local checkpoint as well. And a lot of it gets back to like the flows that they're comfortable with, right? So if you're running Kubernetes on-prem and you're running Kubernetes in cloud and you want to have a single set of mechanisms through which you're using parallel file systems on both, then this just becomes really simple, right? You don't have to rechange to do the ASIC checkpointing aspect or all the different other aspects that come along, right? It really just provides look, it worked over here. We now provide this, make it simple and work out of here. Very little effort is required because the performance is so high in the background.
Hey, Dean,
Yeah.
from a product management standpoint, and maybe one of your compatriots can answer this, why did you guys decide to just release Parallelstore at as small of an offering it is? It's only, you said 100 terabytes is the offering today. Why? That seems, in the world of petabytes right now, what we're talking about for some of the stuff, that seems really like somebody fits on somebody's AI PC computer.
No, it's an interesting question. So some of this gets back to questions around, so you talk to an organization and you say, okay, well, how many nodes do you need? How much capacity do you need? And things like that. And then when you ask them about, okay, well, you have a very specific job. Well, how much data does this one job need? And the answers are strikingly different in many cases. You know, even though an organization might have petabytes of data, any single job, like even a lot of the large LLMs that are out there are only trained on like 20 terabytes of data. It's actually kind of like, it's amazing how much like text data shrinks down to almost nothing. And so in those cases where this is kind of where we decided to focus on, we really get the nice mix of GCS and Parallelstore. So if we think of Parallelstore as the cloud native version of the parallel file system and where we want to evolve it, then its integration with the low cost GCS side is something we really want to leverage. And so you can have petabytes of data in your organization and you can store it at the lowest cost possible in GCS. But then for individual jobs, you know, you can make advantage of this acceleration to really reduce the amount of TCO of the overall job time. Does that make sense?
Mm-hmm.
Yeah. Whereas on the storage scale side, right, it fits more into you can do that integration, but it fits more into the traditional, like, don't worry about where the data is, don't worry about copying it around, just put it all there, right, and it accelerates all of it.
Dean, Max Multilauro here. I do have a question here about what you're presenting. The choices that you have, the decision tree seems to be, you know, rather broad. I would say even maybe a bit complex. I guess that your customers understand, you know, what they want to consume and why, but are you somehow helping them navigate, you know, between these choices and that complexity in terms of assisting them, providing them guidance when they're engaging with you, or are they on their own to figure that out by themselves?
Yeah, well, you know, we're sure hoping to, right? Part of these types of engagements is part of that workflow. As Sean alluded to earlier, we're running a lot of different benchmarks to make the educated decision. So the decision tree that Sean showed earlier in terms of performance, broad stroke performance that narrows into the different solutions. We actually are really working on getting that nailed down to like, oh, you're using JAX with this type of model like that. We've already tried that. We know that this solution will be, you know, the best cost-effective solution for you. And so, yeah, we are back to Dave said, looking at like what consumes his mind, like what consumes our right now is that the portfolio is getting broad. That is an indication of the large number of workloads that we're being thrown at in terms of, you know, a lot of it is where the customers started with and are they born in the cloud, you know, like what type of model with multi-model training coming on to the scene in the last 6 months. Like it has been broad. And so, yeah, part of our role is to help all those customers make sure that they don't have to fail for 6 months before they land on the right solution.
Well,
right? How do we get them to the right solution right off?
A follow-on to that question is, in addition to giving customers a roadmap into what might be the best solution for them, do you also have some sort of guidance on how to cost optimize it for the customers? I realize that for most customers, for customers at this scale, that might not be an issue, but it does seem that you know, coming up with some way to cost optimize it for exactly what they're doing would be worthwhile as well.
Dean, can I take that?
Well, let me just add in a first comment, Dave. So I think that one of the reasons we went with Parallelstore as a Scratch offering initially as well is that Scratch is cheaper than persistent. We can do things on the back end that just does that trade-off. And a lot of the HPC people, but as well as the AI people love that trade-off in the sense that I don't need this thing to be up for 10 years. I'm just trying to run this job for this period of time. Give me the fastest possible thing for that. So that's just some of those decisions that we're making. But yeah, I mean, we think about this all the time. I would love for someone to say, oh, storage is only 2%, so therefore you don't have to worry about cost. They worry about it all the time. And so yeah, thinking about how we customize it, make sure, like I said, making sure all the IOPS are being leveraged, all the bytes are being leveraged, being able, over time, dynamically growing and shrinking as needed. These are all things that are top of mind for us. Sorry, Dave, go ahead as well.
Yeah, I was just going to say I was in a customer advisory board like 2 weeks ago with 20 of our big AI customers, and this is top of mind for them. They definitely want to optimize, but I just want to stress where they're at with their businesses for a lot of the business problems that they're trying to solve. They're just trying to figure out, like, does this work? Like, step one is how fast can I actually put this into production and does it work? And then they want to figure out how to optimize. So what they do want as a very top of mind is please just give us the guidance so that we can get started in the right place. And so it's a huge actually sort of imperative for us. And we didn't by accident think about these workloads like that. These were, actually loading training data, checkpoints, and inference are all like areas where we're investing in benchmarks to really try to lay out that space for customers across all the different products, and then give customers that. Yeah,
I fully expect that it would be a multi-objective optimization that any customer is looking for, but it's if you're only offering guidance on one side of that, on one objective of that, but it sounds like you're offering guidance.
Yeah, we want to do it across the whole product suite. And I'll say too, we talk about it kind of in the stages of the pipeline, like load training data, save check and restore checkpoints, right? Then serve that model. But I will say, like, if you think about the complexity and just where the industry is at, we'll go through I'm probably leading the witness a little bit, but we're going to talk about serving. Serving's actually pretty straightforward from a storage perspective compared to checkpoints and training data. And so we're going to start rolling out like performance data to customers, probably like mostly focusing on inference because we have a very good handle on that. And then checkpoints, I would say, comes next. We have a pretty good idea of what's been happening there. The loading model data, I wish that we had every answer. Like when a customer comes, hey, we want to run Hadoop. We say, okay, turn these 3 knobs. It's very straightforward. But kind of every month, I get a new customer who shows up with a new workload, and we say, tell us what you're doing again. And so I just want to stress, like this market is evolving very, very quickly, still month to month.
So just to say there as well, with the width of the solution base, you must have customers that are coming in saying, I want this. I want option number 2 of 4, right? But you must equally have the same amount of customers that are like, I don't know what I want or what I need or how I get there or what the time to value is there. So how are you managing that? Because certainly in the data analytics world, platforming is a thing right now, right? We used to do one thing, now we're doing lots of things, and then we're doing branches of lots of other things. So how are you, first of all, what are you seeing that in terms of metrics, and how are you managing that? Because to further to Andy's point, it's a thing. Like customers need to understand what that lead time is.
Yeah, it's absolutely a thing. I think the way we try to break it apart as we deal with customers is not think about them as like, here's a customer like with a name, but here's a persona and the job that they're trying to do. So we've been focusing a lot of our research just on understanding how do you get through the whole pipeline by stakeholders. So what does it look like to use storage for the researcher? What does it look like to use and like set up storage for the ML engineer who's building their platform? How does that ML engineer who's building a new MLP take that and combine it with 10 years of data analytics platform work that they've done? That one's like a whole area in and of itself. And so just as this technology sweeps across these organizations, the technology itself is difficult to sort of pick up and use, but it has huge implications for just how they manage and think about data. So all of that is in play here.
So how does inference compare with the training in terms of storage.
That's a great lead into the next section. I might get in trouble for jumping ahead.
You can pay him quarters here.
Let's get to that. I was just going to add into Dave's comment on the last one was, I think one of the amazing things that I've noticed specifically with Google Cloud over the last 7 years is, we don't just throw infrastructure at our customers and then say, okay, good luck, help it. We're really hands-on in all of the engagement. So I really think the AI ML boom that we're currently inside of is really just an evolution of already us working with customers on how to integrate, certain resources like BigQuery with GCS, with all the different types of computes they're looking for. And this is just an extension of that down to the next level to say, okay, now we just have this entire stack, right? How do we make peace of it? And so I think the infrastructure is in place, the people are in place, the knowledge is there. We're just getting more knowledge though, like as we go on, as Dave said, it evolves from month to month.
And as we asked was, go ahead, Dean.
Yeah, no, they're on to serving. Let's do it.
Because, as Dean says, one of the things that when we start to dissect and ask customers, what are their requirements? We ask like, how much throughput do you need? Is your workload random IO or sequential? A lot of times they don't know until they start to run. So it's a little bit of a try, work with this, analyze on the back end. But serving, if you go to the next slide. You're on this. Thanks, Dean.
But that also, Sean, gets into what you were just talking about, the personas, is that most of those guys don't even speak that language. I mean, these two guys don't speak the language that I speak, kind of, more or less.
Very true.
Or that, you and I have spoken. So the personas you're looking at are the ML engineer. You talked about the research. What other personas are you mapping out through what you're offering?
Yeah, so one of the things that we're doing is we're actually working on reference architectures and public documentation so that when the ML engineers are asking certain questions, they can look and understand Cloud Storage Fuse has this type of characteristic, or Parallelstore has this type of characteristics, or the storage team can then relate back to, I know how a PFS environment works. How does that really matter in terms of training and checkpointing when I get asked to provide 100 terabytes to do a job? So it's a little bit about bridging those two personas, because when we talk about customers, even within the organization, sometimes they don't talk directly, or the ML engineer is just like, I don't care. I just need 100 terabytes of storage to go as fast as I want it to. And then it's up to the other team to figure out how do you deliver that. So
if we just take training, in training itself, can there be different requirements from storage perspective based on the applications?
And even within a single customer, if they have 10 different training jobs, Dean was talking about smaller chunks, each of those 10 might be different.
Yeah.
So it's kind of where you get to serving, right? If you're using Cloud Storage Fuse to do training and checkpointing, you're probably going to want to continue to do that for serving, for consistency. And there is a trade-off between trying to optimize each and every one of your training jobs versus the entire environment. And so that's one of the things that if you look at Parallelstore and Store Scale, if you're not using that for training and checkpointing, you're probably not going to use it for serving. You're probably going to use cloud storage, or maybe you use HDML, because Hyperdesk ML can have that very high throughput, 25 hosts with small capacities, because a lot of the models are in the tens of gigabytes in size. And so there are some trade-offs there between optimization, cost, and efficiency.